We want to talk about the molecular structure and the strength of acids. So first of all, when you're talking about the strength of an acid, it's measured by its tendency to ionize. So we start off with something together, and it's going to break apart. The thing you got to keep in mind is these are covalent compounds. So when you actually have something ionize, it's actually breaking a covalent bond. The covalent bond to the hydrogen, but it still is actually breaking a covalent bond. So the easier it ionizes, the stronger the acid. So this is again one of those times in chemistry where we have that higher, lower, stronger, weaker kind of language. That's very important that you practice because it's easy to have the concept right in your mind and get the language backwards. And so two factors are going to influence what we're talking about with this. The strength of the bond between the hydrogen and the rest of the compound, and the polarity of that bond. But before we go any farther, I wanted to get you some sort of an idea what we're really talking about. Because really what matters with both of those, with both the strength of the bond and the polarity of the bond, we're really talking about electron density. We're talking about how well is the hydrogen attached to the rest of the molecule. So one way that you can think about this is you can think about the electron density as being blankets, and you can think about the hydrogen and the rest of the compound as being people. I'll show you what I mean. So we have three different pictures. So in the top left, you can see that there's two people, very nice, equally sharing the blanket. There's an even distribution of electron density over the atoms. So in that particular picture, you couldn't really tell which one is the rest of the compound and which one is the hydrogen because they're so well both covered by the blanket. Then if you look at the one closer to the bottom, you can pick the, I think it's a little boy in the front, who is better covered by the blanket, and the girl in the back that is looking kind of angry that has very little blanket. They both have a blanket. They both have some amount of electron density, but this one we would call a better acid, because that girl in the background is going to lose that blanket fairly easily. She's got a little bit. She's still attached. She still has electron density. She still has blanket, but she doesn't have very much. And then this last one that's on the right, this is actually what it would look like once it's ionized. The blanket is completely on one person, completely not on the other person. So in this case, there's no electron density on the hydrogen. There is all of the electron density on the rest of the molecule. So hopefully this can give you some sort of better idea of what we're talking about. We're trying to predict and describe the probability of the electron density happening in a molecule and how likely it is that our hydrogen is going to become detached from the rest of the molecule. And the way it's going to stay attached or become detached is all based on electron density. Or, for this analogy, blankets. Figure that with the snow outside and the weather that blankets might be a good analogy. So the first one we want to talk about are binary acids. So this is hydrogen and a nonmetal, and that's it. So what we're talking about is, and we can talk more about hydrohalic acids, which are binary acids with hydrogen as in the halogens. And so you've got sets of these. So the first thing we want to talk about really is when you go from left to right. So as you go from left to right, you actually get a stronger acid because you're getting a more polar bond. The more polar the bond, the more ionic character it's got, the more easily ionizable it is. So in this case, we're trying to do things like compare fluorine and oxygen. We're trying to compare chlorine to sulfur. We're trying to compare them left to right as we go across. Because the one that you might be more familiar with is the other one, where we compare top to bottom. And top to bottom sometimes is a little bit more difficult to understand. But as we go from the top to the bottom, you get a stronger acid. And this is actually what explains why we have hydrochloric acid and hydrobromic acid and hydroiodic acid, and those are all three strong acids, but hydrofluoric acid's not a strong acid. So what's happening is, if you'll recall back to yet another periodic trend, we have things, not only electronegativity, but we also have things like electron affinity. And with some of these other things, it actually describes how well can an atom hold on to something that's on its outer valence. And the truth is that the farther down you go, the weaker the bond is. The farther down you go, the farther there's a difference between the nucleus and its outermost electrons, and the worse the atom is at actually holding on to anything. And here's some bond enthalpies to show you that a little bit better. Basically, the stronger the bond, so the larger the number, the weaker the acid. So that hydrogen is holding, that fluorine is holding on to that hydrogen really, really well. The chlorine, not as much. The bromine, not as much. The iodine, not nearly as well. So since they're not holding on to that hydrogen as well, they're going to be able to let it go much easier. They're going to be able to ionize much better. I'm going to leave oxoacids for a different video.